In 2020, everyone declared the convolutional neural network dead. Transformers had arrived, and they were eating everything in sight. But a team of Facebook AI wasn't so sure. What if convolutions were actually inferior, just under-modernized? To understand why this question matters, we need to go back to 2020. For over a decade, convolutional networks dominated computer vision. AlexNet, VGGNet, ResNet, EfficientNet. The list of breakthroughs was relentless. Then, in 2020, Dosovitsky and colleagues asked a radical question. What if we just cut an image into patches and fed them straight to a transformer? Vision Transformer, VIT, matched ResNets when trained on enough data. Then, in late 2021, the Swin transformer did something interesting. It borrowed back ideas from ConvNeXt, locality, hierarchy, sliding windows. Swin hit 87.3% on ImageNet and dominated detection and segmentation benchmarks. But the Facebook AI team looked at Swin and saw something different. They saw ConvNeXt priors hiding inside a transformer wrapper. So they asked, what happens if we modernize a plain ResNet the same way? Every great advance starts with an honest baseline. For ConvNeXt, that baseline is ResNet 50, the workhorse of the ConvNeXt world. The original ResNet 50, trained for 90 epochs, hit 76.1% top 1 accuracy on ImageNet. A respectable number. But that was back in 2015, with 2015-ER, a training. The ConvNeXt authors asked, what if we just trained ResNet 50 the modern way? Step 1. Train for 300 epochs instead of 90. More iterations, more learning. Step 2. Swap SGD for Atom W, the optimizer the transformers swear by. Step 3. A full battery of modern data augmentations, mix-up, cut-mix, rand augment. Stochastic depth randomly drops entire layers, acting like a powerful regularizer. Label smoothing stops the model from being overconfident in its predictions. 6 techniques, all borrowed from the transformer playbook. The result? ResNet 50 jumps from 76.1 to 78.8%. A 2.7% gain from the exact same architecture, just trained better. This is a profound lesson. Training methodology is architecture. 78.8% is now the new baseline, the floor, not the ceiling. Now the real surgery begins, changing the architecture itself. First question: how do you divide computation across a network's 4 stages? ResNet uses a 3-4-6-3 pattern. Most compute in stages 2 and 3. Swin transformer uses a very different 1-1-3-1 ratio across its stages. The insight: Swin concentrates a 3-to-1 ratio in its 3rd stage. ConvNeXt adopts a 3-3-9-3 distribution, following Swin's lead. Stage 3 now carries 9 blocks, most of the network's heavy lifting. This single change pushes accuracy from 78.8% to 79.4%. Next, how does the network first process an image? ResNet uses a 7x7 convolution with stride 2, followed by max pooling. That aggressive downsampling discards spatial detail before learning even begins. Vision transformers took a cleaner approach, non-overlapping 4x4 patches. ConvNeXt replaces the old stem with a single 4x4 stride 4 convolution. One clean step. No max pooling. No information thrown away early. The result: accuracy climbs another notch to 79.5%. Flops drop slightly to 4.42 billion. These macro changes answer a key question: where should computation live? From 76.1% to 79.5%, and we haven't touched a single activation or kernel yet. Next, we go inside the residual block and change everything. ConvNeXt rebuilds the ResNet block, one surgical change at a time. First, replace standard 3x3 convolutions with Depthwise convolutions. Standard convolution mixes spatial and channel information simultaneously. Depthwise convolution separates them. Each filter handles exactly one channel. Sound familiar? That is exactly how transformers work. Self-attention weights positions spatially. Depthwise con weights positions spatially. To recover capacity lost from fewer parameters, width increases from 64 to 96 channels. Result: accuracy climbs from 79.5% to 80.5%. We are already ahead of Swin T. Next change: flip the bottleneck structure inside out. Standard ResNet bottlenecks go wide, then narrow, then wide again. ConvNeXt inverts this: narrow, then expand wide, then contract back. This mirrors the transformer FFN exactly. Expand 4 times, then project back down. Accuracy ticks up to 80.6%, while flops drop from 5.27 to 4.64 billion. Efficiency win. Now comes the counterintuitive move. Relocate the depthwise con upward. Transformers do multi-head attention before the FFN, MSA, first, and LP second. So, spatial mixing first, channel mixing second. ConvNeXt follows the same order. Accuracy dips to 79.9% temporarily, but this unlocks the next upgrade. Now that the depthwise conv is isolated, we can grow its kernel to 7x7. Swin transformer uses 7x7 local windows. ConvNeXt matches that receptive field. Because depthwise conv is cheap, this larger kernel barely increases compute. Accuracy recovers to 80.6%, matching the inverted bottleneck result, but now with fewer flops. Step back. The whole block now looks structurally like a transformer layer. ConvNeXt achieves spatial channel separation using convolutions, not attention. These are the macro structural choices. Next, the micro design details that seal the deal. We are down to the final polish, micro design decisions that compound beautifully. First, swap ReLU for GELU, the smooth activation transformers rely on. Accuracy stays at 80.6%. GELU alone is not the unlock. But what happens when we remove most of those activation functions? The transformer FFN block has exactly one activation inside the expansion. ConvNeXt trims to match one GELU after the expanding 1x1 Conv. 80.6% jumps to 81.3%. That is plus 0.7% from removing activations. Less normalization next. Keep only one layer norm before the depthwise con. A modest but real gain, 81.3%, rises to 81.4%. Now the sacred cow. Batch norm has defined convets for nearly a decade. Replace it with layer norm, the normalization transformers use, and it works. 81.4% to 81.5%. Proving layer norm is not just a transformer-only trick. The final move. Pull down, sampling out of the residual block entirely. Layer norm, then a 2x2 stride 2 conv, clean, explicit, and stable. 81.5%, leaks to 82%. A half-point gain from one structural change. Here is the final ConvNeXt block in its entirety, clean and elegant. 1.4% total, from micro polish alone. Now let us see the results. ConvNeXt ships in 5 sizes, scaling from tiny to extra large. From 29 million to 350 million parameters, a complete family for every compute budget. The real test: can ConvNeXt beat the Swin transformer head-to-head? ConvNeXt scores 82.1%, beating Swin T's 81.3% at identical cost. At the base scale with 384 pixel inputs, ConvNeXt B hits 85.1% to Swin B's 84.5%. ConvNeXt wins at every single scale, and it's not even close. Pre-trained on ImageNet 22K, ConvNeXt Extra Large reaches 87.8% top 1 accuracy. But ImageNet is just one benchmark. What about real-world tasks? On COCO object detection with Cascade Mask RCNN, ConvNeXt B scores 54 amps/p. ConvNeXt L pushes to 54.8 amps/p. Box, beating Swin L at 53.9. On ADE 20K semantic segmentation, ConvNeXt B achieves 53.1 mean IOU versus Swin B's 51.7. ConvNeXt Extra Large reaches 54 mean IOU, again ahead of every Swin counterpart. Even without hierarchical structure, ConvNeXt holds its own against VIT. Isotropic ConvNeXt B scores 82%, just edging VIT B at 81.8%. Then one more thing: ConvNeXt is also faster than Swin at every scale. Step back and see the full journey. ResNet-50 at 76.1%. Modern training recipes alone pushed it to 78.8%. No architecture changes. Then, one deliberate design choice at a time. ConvNeXt T reached 82%. No attention mechanisms. No self-supervised pre-training. Just principled design. The lesson: don't throw the baby out with the bathwater. ConvNeXts were never the problem. Outdated design choices were. In 2023, ConvNeXt V2 arrived, combining masked autoencoders to reach 88.9%. Today, over 150 ConvNeXt model variants live on Hugging Face, widely adopted in industry. Good design principles outlast any single architecture hype cycle. The next breakthrough won't come from chasing trends. It will come from understanding fundamentals.